Hi, everyone. Welcome to our Academic Innovation Support live stream at Wolfram Research. Joining us today is Michael from Q-CTRL and Mats from Wolfram Research Quantum Team. I am the program manager at Academic Innovation Support Team from Wolfram Research. Personally, I'm so excited to have this conversation happen. If you are already following our LinkedIn page, you will see the countdown pages every day for this conversation. So now I will hand the headphone to Matt and Michael.
Thank you, Yi, for the introduction. Hello, everyone. We are very happy to have Michael Hodge, who is the Chief Scientific Officer at Q-CTRL, joining us live from Sydney. Good morning, Michael.
Morning slash afternoon slash wherever you are, different time zones, I guess. Yeah. So, hi everybody. I'm Michael Hush. Yeah, Chief Scientist at Q-CTRL. Been working in the quantum industry since I could study, and but specifically at Q-CTRL for the last 6 years, and then did some research beforehand in the last 15 years. So,
Awesome.
Yeah, glad to be here and keen to talk about quantum computing.
Thanks for accepting our invitation. During American Physical Society March meeting 2024, Wolfram Research together with Q-CTRL, we had a big announcement that received lots of attention. We announced our strategic partnership together with Q-CTRL, and we released the integration of one of the products of Q-CTRL together with Wolfram Quantum Framework, and that product is FireOpal. And today we are going to talk about FireOpal. But before talking about that very specific product, so let me start with providing the big picture for our audience. And I would like to hear your thought, Michael, on that. So we know that one of the big questions that we have is how to scale up quantum systems. And by quantum system, I mean the actual quantum hardware, because that's the only way that we can solve hard, important problems. So we need basically many, many qubits, and likewise, based on that, we can create our logical qubits. There are promising technologies out there. We have superconducting qubits, we have trap ion, trap atoms, we have spin qubits, we have photonics. Which one will be the leading technology? We don't know yet, but everybody knows that in order to achieve that quantum value, we must follow the approach of fault-tolerant quantum computing. So when we talk about fault-tolerant quantum computing, what do we mean by that?
Yeah, when we're talking about fault-tolerant quantum computing, I think the key thing we're talking about is you're using more than one qubit to encode the state, and you're doing it in such a way that you can correct errors that occur. So well, I think there's an idea out there that if you can correct faster than the errors are occurring, you might be able to have a qubit that lasts for a long time. In practice, what we expect at Q-CTRL is just it's another technique you're throwing into the mix. So what fault-tolerant quantum computer, what the early generations will do, will be able to do computations for much, much longer. And so that's the big game you're really playing, is lots of different techniques being added onto your device so that you can remove errors, so either stop them from happening or correct them after they occur, so that you can do computations for longer, which provide bigger value using more qubits. Yeah.
Excellent. So I'm going to go ahead sharing my screen, just showing our audience what we are talking about. So this was basically our announcement for APS March meeting, which was the integration of FireOpal together with Wolfram Mathematica. And what's happening here, we can show it from one specific example. So what you see here is the prediction, is actually the results that one get from a very specific quantum circuit. This is a phase estimation quantum circuit. On the top, you see the prediction of quantum. For those of you who are not that much familiar, phase estimation is a very important ingredient that we have in many quantum algorithms. So for us, this very specific, distribution, especially this maximum peak, is important. And if you send your circuit, which is basically, this is the circuit that we have, basically a collection of quantum operators on different qubits. If you send it to, one of the available quantum processing units, even the best ones that are out there, the lower bar chart, that's the result that you get from the hardware. And if you compare it with the one that is the expected value from the theory, you cannot get that much meaningful result from this experimental data. No good. But if you incorporate, fire opal, you would see a very, even like, without doing any statistical, like, analysis, people by just eyeballing, you can see the big improvement if somebody used like, fire opal. So, Michael, help us to understand better. So what happens when we create, a circuit like this, and when we feed it to fire opal? What fire opal does that we can see, like, an improvement in the performance of the hardware?
Yeah, so to begin with, you got to talk a little bit about the problems that occur. So when you apply it, when you send those gates to a quantum computer, they're implemented using some physical process. So if you're a superconducting device, you've got like a Cooper pair spinning in a particular direction, and you're applying some microwave pulse. The challenge is those gates are imperfect. And they might leak to other qubits. They might send a signal to the qubit they're not trying to send a signal to. They might not quite do this right operation. Or there might be, the qubits sometimes are not perfect and they might leak into the environment. There are all these different things that can ultimately cause errors. So what that means is when those errors occur, it will give you the wrong result. And the challenge is when you're using a quantum computer that is available today, you don't necessarily also know if you're getting a wrong result. So it's not telling you that things have gone wrong. So what we do at Q-Control is we're integrating every piece of state-of-the-art technology to remove errors. So what you're seeing here uses what we call error suppression. And error suppression is a technique that you will want to use with full-fledged error correction. But until full-fledged error correction gives a benefit, error suppression is a great technique that you can use to get huge improvements. So error suppression uses our understanding of the physics in the device to actually eliminate the errors before they occur. So how we do that is that we change the sequence of the microwave pulses that are applied. We change their shaping. We basically create interactions on the device which remove the errors that occur as the process is going on. They effectively cancel themselves out. And so by doing that, by suppressing those errors basically before they contribute to the final result, as you can see, you get a much better answer. It allows you to get the answer quicker with less executions. And there are other cases, which I'll probably show later, where it can even change the device from giving the completely wrong result to the correct result. So it's really important to use the best techniques available when you're trying to use a quantum computer to get the right answer.
So basically, like, a circuit like this, which is basically a collection of like, quantum gates, like, in this case, all of them are unitary operators. And at the very end, we do the measurement. So at the level of hardwares, like, for this case, let's talk about like, superconducting qubits. So what the hardware understands is basically a sequence of pulses, right? Like, different, like, different, in different locations in time, different pulses. So when we use fire opal, we are not changing this circuit. It's not like, creating a new circuit, etc. Basically, what is happening is mostly a sophisticated way of like, when to send those pulses. Like, basically it's like, I'm going to pause at the right time, and then I'm going to send like, the signal, the pulse that's corresponding to one of these gates, right?
Yeah, there's a slight subtlety I'll add to. So you're executing the same circuit. So the logic is the same, so to speak. The other thing that Q-Control's fire opal does is, in practice, the qubits aren't connected in the way that they are in this diagram. So when I draw a normal quantum circuit, I can apply a control gate to any other qubit, no hassles. The reality of the device is that each qubit is actually physically located in such a way that on a superconducting device, they can only communicate to the ones that they're neighboring. And there will only ever be like 2 to 3 qubits next to each other on most devices you can get access today. So in order to do a circuit like this, you actually have to like shuffle around the information on the qubits, or you might have to change the way the gates are implemented so that you might use one which is one thing we call like a native gate. So the actual pulse that's applied versus the abstract one that you see here. So in any case, getting this ideal circuit and turning it into what's implemented on the machine is called compilation. And we also have really sophisticated subcompilation techniques. So that means that when you use a fire opal, it'll also often be a shorter physical circuit that's implemented because we're able to figure out how to compile it better for the machine itself.
So, like, before we jump to the details of, like, how firewall works, like, again, like, a quick reminder to our audience, like, the big picture. So what you can do is, like, you can create your circuit in Mathematica. The quantum prediction is like, these are the results, like basically what quantum theory, like, tells you, like, what are the expected probability distribution. But because of the noise, the best hardware that are available out there, like, here we are talking about digital quantum processing units, you cannot get a good result. So you need other techniques. You need to take care of the noise. Okay. So in this case, like, noise suppression is one of the many techniques available out there. Of course, we know that the full scale, the quantum fault-tolerant quantum computing, we are not there yet. We will discuss very soon, like, what's the future is gonna look like. But at least we can get meaningful result from the current, like, hardwares that we have out there. So that's basically the big picture. Now, Michael, let's jump in. Let us understand, more details. Tell us more details, like, how firewall works.
Yeah, so I guess the maybe bringing it back to what you're trying to do with a quantum computer, because I'll talk a little bit more about what the applications are, I think. So Firewall is attempting, what we do is we try to bring control techniques into where we're seeing people use quantum computers most. And so we've noticed there is like a really serious trend for people trying to use it for optimization of like logistics problems or optimizations of quantum chemistry problems. So what's going on at the moment is people are trying to use quantum computers in a way where you can leverage the strength of a quantum computer. So like put the processing that it's good at onto the device, and then combine that with as much classical processing as you can do. And examples of algorithms like this are called the quantum Q808, the quantum approximate, what was it called? I used that term, so I forgot the name of it. But another one is like VQE, variational quantum eigenstate solver. So these are techniques which allow you to find ground states of quantum systems, but you can link that to physical processes. So you might have a set of delivery points you're looking for. You're trying to find the best way to send out your trucks to get parcels to people. That problem is really hard. It's called an NP-complete problem. So the best you can hope for is an approximate solution, but there are definitely good, strong suggestions out there that a quantum computer may be able to get a better approximate solution faster than the best approximate solutions that we currently use. So that's an example where we're seeing a potential for an advantage with a quantum computer. But the challenge is when you try and run that, if you don't use the right control techniques, if you have errors, you will find that as you run your quantum computer in the classical computer loop, as they're trying to solve this problem, as they're testing out optimization challenges, it will take too long. It will keep providing the wrong answer, keep searching, because those errors will lead it astray. It'll send it off in a direction where it shouldn't go to. So we innovate kind of everywhere we can. So with regard to those closed loop optimization problems, we have a package which is designed to do optimization problems as well. And that allows you to, it takes into account the way in which you measure success each round. We improve the cost function it optimizes. We again remove errors using error suppression. And we also fix the measurement stage. So at the end, when you take a measurement, the measurements are never quite perfect. And you can actually do corrections called measurement mitigation techniques to improve the distribution that you get as well. So that all comes together. It's very complicated, it sounds very complicated, sophisticated, but ultimately, the great thing with the integration with Mathematica is you get to program your quantum computer in a really interactive, visual way. It's so much quicker to learn, right? When you can just create a circuit diagram in a single command. And that's like what I love about Wolfram products is it's just so quick to get that visual information, right? But then combining it with Firewall, it'll reduce the number of times you have to execute before you get to the right answer. And it should also provide the right answer when you would otherwise get noise. So that's what we're hoping to provide with this combination, is that speed of iteration where you can really just experiment and learn using Mathematica combined with some more reliable outputs from Firewall. Yeah.
So to clarify, one thing, like, when we talk about like, improvement, like, by incorporating, quantum processing unit, this improvement, in the literature, when people talk about like, quantum advantage, that has a very specific meaning. So like one thing we would like to clarify is improvement happens at many different scales. Like, it could be, for example, comparing to a classical optimization technique, it could be maybe 10 to 12% improvement. But it's still like, when we look at the scale of the problem that you want to solve, like, the army deployment case that you mentioned, or like, the logistics type of problems that you mentioned, given the scale of those problems, even a tiny quantum value, 10%, 12%, not the exponential. This is not what people would call as a quantum advantage, but that is still a big deal. And this is the part that I think like in our audience, they should keep that in mind. Like, many of these algorithms, they might not provide a true quantum advantage in a sense that like, theoretical computer scientists would call it quantum advantage, but still they provide a very good improvement. Would you like to elaborate a bit more on like what do we mean by like improvement by incorporating quantum?
Yeah, I think that's it's something we talk about a lot in house as well at Q-Control. So like you were alluding to, there are certain proofs for very specific problems where you can prove this like exponential scaling advantage, like prime factorization, which is relevant to cryptography, right? Indeed. So in the long term, that gives you like some really solid foundations that eventually, if you build a quantum computer big enough, it will be able to provide an advantage. But the challenge is that that goal is really, really big. It's a huge effort we have to put in. And it seems like it's definitely going to require fault tolerance, right? So some of the nearer term opportunities look like what can we do with the devices that we have today, which are starting to get to a size where you can't easily simulate them on a classical computer. So do you mind if I speak a little bit about that difference first?
Please.
So yeah, I think like when I started in quantum computing 6 years ago, the devices that were available, like from IBM and other providers, they were great. It's great to have access. It was great to be able to experiment with real machines. But if I gave one of my undergrad students at the time and asked them, "Can you go simulate this?" they could get their laptop and simulate that quantum computer in 5 seconds. Like it was these qubit and 5 to 6 to 7 qubit devices. They were great to start learning, but they just didn't provide much of a value compared to what a student could just do themselves. The big change that we're seeing now is that the devices that are being produced, so IBM is producing devices with 127 qubits, you're not necessarily you can't necessarily execute an arbitrary program. So the challenges with the bigger devices is that the error rate means that you have to effectively do shorter circuits. So the algorithms that can typically use a lot of qubits because they go fairly deep, they're harder to run. And instead, you typically want to run circuits which are relatively shallow, but can connect, in principle, as 127 qubits. So the interesting thing that's happening now is if I was to tell my undergrad, go and simulate 127 qubits, there's no way they could ever do that on their laptop. The size using completely standard textbook out of the textbook techniques to simulate a quantum computer are no longer able to keep up with devices that are available. What's changed is now the world's absolute experts who have spent years figuring out techniques and how to simulate quantum systems at their very best, they're the ones who are competing with what the quantum computers can do today. So it has been a real significant shift in the technology where it's been from what we, as physicists, would call toy systems to quantum computers, which are pushing the edge of our limits of understanding of classical simulation of quantum devices. So, and that's a really interesting place to be at. So going back to your question about applications, the thing that I think is interesting to consider now is trying to look for those real potential practical advantages on devices that you can access today. And so you can't do those experiments with just a scaling argument mathematically, because you have to take into account the practicality. You have to take into account the speed of the gates, the number of the number of errors that are occurring. You have to experiment with real devices. And that's what I think is like a really interesting space to be working right now, is finding problems, seeing how they fit on devices today, and then looking forward to see when there might be an advantage for that particular problem, which you would prove more in practice using real device time rather than trying to do a mathematical proof. There's a space for both of those places. There's a space for both, obviously, and it's good to have both of them pushing the industry forward. That's just because we at Q-Control love using real devices, so we're often also just really experimenting at that near term, because it's just where we think have the most fun, so to speak. Quantum computers are a fascinating, complicated device, so they're it's good to try and figure out how to make them better.
So I know you put together a very nice slides that you wanted to share with our audience. You know, you can go ahead, share your screen. You had some of those interesting applications that you wanted to show. So let's go through that and let's discuss that.
Yes, okay, hopefully everyone can see that. So we're just to open. So again, thanks so much for the opportunity to present here and talk more about our integration. So yeah, you can tell that this is actually my generic pitch deck, by the way. So let me just speak a little bit more. So we've talked a little bit about this already, but there is a really big opportunity in quantum computing. There's applications all the way through from quantum chemistry to logistics optimizations, as we said, but it's also going to have an impact on how we protect our information. So there's the potential impact on the cryptographic techniques we use. It's a technology which could really change the nature of compute. And I guess in the bigger picture now, as we're seeing so much interest in AI, etc., there's this real need and push to push our boundaries of how much compute we can get more efficiently from the devices we make. And I really see quantum computing as a part of that. There's still not a clear answer exactly of how quantum computing will interact with machine learning. That is one of like the really interesting questions. But at the very least, you really should think about quantum computing as like another avenue in which we're trying to push compute to its absolute limit. So what is the problem right now that's occurring with these devices? So the challenge is, if I try and run an algorithm today on a quantum computer, as we talked about, there are a lot of errors. And those errors can be so bad that they can wipe the correct answer off altogether. So just here on the right is a search algorithm example, Grover search. You can see that what we're expecting to see is a peak with the answer we're looking for. So you're searching for the database and trying to get out a bit string corresponding to what you are looking, not a database, sorry, like a set of information you're trying to find. The default settings on a quantum computer, sometimes the errors can be so large that that correct answer is not only the small, it's one of the smallest of the probability of the bit strings that come out. So on the bottom, you can see again, with using our FireOpal toolset, we can suppress errors and mitigate errors at the same using the same toolchain to increase the chance of seeing the right answer. And so in this particular case, this is data from a real device. You can see we've boosted the probability of getting the correct answer all the way to it becoming the dominant mode, and so the correct answer is restored. So by building this technology and making it available online, which allows other people to also test and verify its performance, we've made a lot of progress in moving forward with FireOpal. So just as an example, IBM has then taken this technology with us and embedded it onto their hardware as well, so which provides even better results. And that's shown on the right with the kind of advantages we can get with particular algorithms. We can really boost the probability of getting the right answer, which can ensure that you're getting the most value you can from the devices that you're using. So to go back, I've kind of mentioned bits and pieces of this throughout the presentation so far, but just to kind of give you the full picture of all the components that go into the FireOpal chain. First, we compile it for the physical device. So we ensure that the number of physical gates that are used actually is minimized, and we ensure that the circuit that is executed is done as quick as possible. Then we actually use a error-aware hardware mapping. So this uses an understanding of how the gates are operating, which ones are operating where, to figure out how to remove errors. So we then interlace a variety of correction techniques across the circuit so that errors like crosstalk are effectively cancelled out completely. And then finally, we also actually optimize the shape of the individual pulses. We do that using a regular calibration routine to ensure that individual gate performance is better. Finally, so that's run on the computer, and the computer will then make a variety of measurements. The measurement stage also is imperfect. So we finally have an error mitigation technique that corrects the errors, that corrects some of the errors that occur due to the measurement part of the process, not just the computation. And those results are then returned to the user. Using those techniques, so I think the thing that I really wanted to highlight here is using these techniques, you can see that the success probability as we increase the depth of the circuit. So using Q-CTRL here on the top is the purple line. So you can see that the probability of it giving the right answer stays higher for much, much longer than it does without the control techniques we provide. I did really want to highlight here, though, it's not flat. So you're going to eliminate as much error as possible, but there are certain processes you can't fix. So, for example, crosstalk, where qubits are accidentally talking to one another, that's something we can basically almost entirely eliminate. The problem that can't be eliminated is when individual qubits just leak. So they basically send information out into the environment. It's the quantum way of saying it, but in a physical process, it's like it relaxes. You lose some of that excitational thing. It goes into the system, goes into the material. So that's called a T1 process. That is the type of error process that you can't correct with error suppression techniques. So there's still a limit to how deep you can run your circuits before you get the wrong answer. And that is where we would look to quantum error correction techniques to then put on top of these techniques we've talked about today to help correct that error process. So also stay tuned. We're always improving FireOpal, always looking to integrate in new techniques, always trying to push it further and further.
So Michael, if you go back to the previous slide, how sensitive is FireOpal algorithm with respect to a specific backend that the user picks? Basically hardware by hardware, do we see a different performance, or on average, we should be able to see a good improvement in any backend that we pick?
Yes. So we only ever put backends up online where we can see a significant improvement. There is small variation between different devices, but I'd say largely we get comparable performance. We work hard to make sure that the techniques that we've developed are all implemented correctly for the particular device that it's running on, so that you're getting a comparable improvement in performance. So that says, that's also because we have been, I think at the moment, primarily there are superconducting devices that are available on the platform. So as we move forward and we start making more different physical systems available, so we're looking to put ion systems up online and Rydberg arrays as well, that will create probably quite different expectations of improvements of performance, because when you've got radically different hardware platforms, the way in which the correction and error suppression occurs is really changes. But we live by a mantra of always improve. So you're always going to get an improvement with FireOpal. We just make sure it never disadvantages you. And if you're using a device of the same nature, so all superconducting devices at the moment, they all pretty much reflect each other in terms of the amount of performance that you're going to get.
By the way, for our audience, I know, Michael, for your information, every summer we have a very large summer school, and one topic that more recently our students, we call them students, but they come from all different level of academia and also industry. So for them, listen very carefully, during the summer school, when we discuss, more, you are going to use many of these tool sets in order to perform algorithms on the real hardware. Another question, not a question, reminder for our users, like, you can see it both if you use directly FireOpal or if you use it in Mathematica. Whenever you send any job to any hardware, if the specification of that hardware is in a way that, like, you might not be expecting a good improvement by using FireOpal will give you some alarming messages telling you, look, the hardware that you are using, it has this error rates, and within this error rates, do not expect like a big improvement or such. So I just wanted, like, to bring, like, to our audience attention that, like, read those, like, detail, like, messages. They are very helpful.
Yeah, that's I think that's one of my favorite features of FireOpal, because it's always nice when an error message gives you value. It's just like, as someone who's like always trying to make good products, I love it when that occurs. So yeah, that was really important to us. And you're like, on this plot, it's basically, if you go too far to the right, we tell the users, like, just don't waste your money. Just please shorten your circuit, because you don't want to do an execution that isn't going to give you a meaningful answer. Yeah. So I'll just briefly finish up on some of the applications that we're looking at. So yeah, as I mentioned earlier, one application of quantum computing where you're trying to leverage the advantages of your quantum computer and then supplement it with as much classical compute as possible is these solvers like QAOA or VQE, where you put the quantum computer in a loop with a classical computer and you ask it to optimize a particular control problem. So that basically ends up, you take a graph which represents your particular optimization or logistics problem, you feed it, you then have a translation layer which changes that into a set of quantum circuits which you're optimizing. And that can be useful for providing insights into particular problems. So on the right is an example where we've looked at transport challenges, and basically we've got convoys where you need to get from A to B. You can have really interesting, challenging constraints, like the particular order may be important when you're trying to optimize these things. We've been looking at optimization problems which have like direct relevance to real business cases. And so you can translate that kind of optimization problem into a quantum computing algorithm and then execute it. So, and just to speak to the earlier point, yeah, so you're not expecting to see quantum advantage right now today with these problems compared to state-of-the-art solvers. But what we've been doing is we've been looking at how close they are getting and trying to figure out where there are bigger opportunities. So at the very least, we can say that it seems like you need like 300 to 400 high quality qubits before you get into a regime where the classical solvers for these kind of problems are failing enough that there's a gap. There's a sufficient gap that a quantum computer may have an opportunity to actually compete and provide an improvement. So that just is an idea to give you the kind of scale of where you need to get to. But when I said 300 to 400, it's not just raw qubits. They do have to have a high quality. Basically, the error rate has to be low. So just this is an example of us using our control techniques to see a real quantum difference when it comes to solving a particular optimization challenge. So, and as far as we're aware, this is the biggest demonstration of using QAOA to solve a max cut problem. So the most we could push the current devices that are available, so there are 127 qubit devices, but the maximum we could get to was 70 qubits, was the amount of qubits in this actual graph which we solved. And what we did is we put in a optimization problem where you're trying to solve this thing called max cut. So basically trying to find a series of cuts across the graph so that you've got the maximum amount of clustering. So what you can see here on the right, what's the most important here is that what we did is we considered just like a classical random sampling, so that we call that brute force. And that shows you on the left the distribution of answers you would get if you classically just randomly sampled the graph. And what we're showing on the right is after a handful of operations using QAOA in that closed loop, at the end, that is the distribution we got from the quantum computer with the modified parameters that are being optimized. And you can see that it's correctly and effectively with that search process shifted that distribution. So you're now able to find the maximum cut solution with a high probability, which is actually 95 in this case. So it's effectively learnt and pushed that distribution.
So one side note regarding like, this whole, quantum optimization problems, in particular, like, application for the max cut. All of them are like, for many of them, there are available classical algorithms. Like, these are like, many of these problems are like, famous, like, classical optimization problems. And when we talk about like, adding quantum flavor into that, are we really talking about like, quantum flavor as if the algorithm is classical quantum hybrid, or we are talking about like, 100% quantum approach to solve the same problem?
Yeah, so what you want to be comparing to is the state-of-the-art classical solver, but the challenge is often that the way in which the classical solvers solve a problem compared to the quantum approach is just so radically different. It's very hard to do head-to-head comparisons other than just timing. So you just run them both and you say one's faster than the other. So I do want to say that's not what we're trying to show here. So that brute force is not meant to be like the classical best. It's what we're doing here is just saying, is the quantum computer doing anything? So there is this element where you really want to make sure when you're also doing these optimization algorithms that the quantum aspect is contributing, because you can access, if you're not doing a good job with this, you can do QAOA optimization where the quantum computer is actually, so many errors are occurring, it's almost classical, but it's still trying to do some learning based on the classical information that it's randomly sampling. And so QAOA sometimes can, particularly for smaller size circuits, may converge even though you've got not a lot of quantum going on. So what we're doing here is we're just really showing that the quantum component in the process is making a really big difference. It's actually moving it to a better solution. And then we're giving some kind of understanding of how much improvement that has occurred. In terms of comparing to state-of-the-art, this is not faster than state-of-the-art. And particularly for max cut, I think the estimates that last time I looked is you have to go higher. I think it's like 800 to 1,000 or 1,100. Like those are the kind of estimates of the number of high quality qubits you would need before you'd be competitive with classical heuristics. So again, I just wanted to highlight, it does matter what particular optimization problem you're looking at. So the one I was showing before is what we call it's a highly constrained optimization problems. So highly constrained optimization problems can be the case where there does exist a bigger gap where the classical heuristics are beginning to fail, while max cut is a relatively simple optimization problem. So the quantum computer is really going to have to be pushed a lot further in order to be competitive with the best solver for that case. Yeah.
Yeah, in fact, like, go
sorry,
ahead.
I was just going to say that finishes the presentation. So I can go back and if you got any further questions on that last one, happy to address it. Yeah.
Awesome. So like, we are, as we were discussing, like, there has been like, a couple of questions, and like, I was trying to provide like, the some relevant links, for those questions. So as Michael said, like, there are some, like, the whole literature, or like, the way that, people are talking about like, quantum utilities or quantum applications, sometimes like, the true description, it could be misleading. And like, what Michael explained here is basically like very to the truth of what we can get, what type of value we can get if you include like, some quantumness into your algorithms. We are well aware that like, some of those algorithms, the state of the art of classical optimization problems, they perform better. But like, we are like, right now we are like, at 60s, 70s, the time that like, people just started exploring like, classical computers, and nobody knew like, what they can get out of that. And some of like, those algorithms, God knows like, how much it's going to take just to run that. But once we learn how to do those simple cases, we can like, scale it up very fast, and we can like, bring the true quantum advantage. So in terms of like, applications, Michael, optimization is like a big topic. Like, many people, they talk about like, optimization type of problems. What other quantum applications are out there that like, quantum method can bring true value in addition to
Yeah.
optimization?
Yeah, I think that's it's a really big question which we think about a lot. So there's a lot of interest in the intersection between quantum computing and machine learning. So we continue to do our best to support people who are doing research themselves on quantum machine learning. So far, it is a really interesting topic in that in the literature, you can see there are very clear evidence that quantum machine learning, when you're trying to learn quantum states, does appear to have this certain advantage. But what's challenging is that the reality is anyone who's trying to use machine learning at the moment in any commercial sense, they have real information, they've got real data. And the other thing is they want to know the answer. So they want to measure it. So they can't keep their data quantum, so to speak. And so that's the real push, I think. And in that case, we just don't know. We're just experimenting, right? So I would say, first and foremost, I'd say one should be experimenting. Like there is a really interesting turning point we're going right now where you can be doing experiments, you can be exploring these problems, but you've always got to be honest and clear with the people you're working with, right? Because you've got to put in go and no go. So that's like a big thing that I would recommend for everybody is just don't try and implement a full-scale solution with a quantum computer. Never promise this. That's madness. The technology isn't in that state. Instead, you really got to be telling people if they're interested in learning about quantum computing, if they're interested in trying to investigate cases, go through a process with them. So do some small-scale experiments and put in go or no-go points where you put a real quantitative check if that quantum computer is going to give an advantage against what you've considered the appropriate classical benchmark, and you don't implement a solution until you do those checks. Like that's very, very important. In terms of other applications, I think I'm trying to think of the things that we do a lot. I think so. Quantum chemistry also continues to be something which we're seeing a lot of traction in that in Japan as well. Like a real interest in doing a lot of quantum chemistry is bubbling up there. Yeah, we've been doing our best to improve closed loop optimizations, which are relevant to those problems. That's another really interesting place where I think the big push there is really finding that intersection of like quantum chemistry experts who can find those problems which we haven't figured out yet, which may be able to be executed on a smaller scale and more relevant scale. But the quantum chemistry challenges at the moment look big that you need to do before you get to the potential place where they'll have an impact. So that's definitely a place where we're doing a lot of supportive experimentation, but I don't expect to see that in the near term. Although I would say there are people out there, again, experimenting with machine learning techniques in that tool chain. So some people are not trying to necessarily completely take on the full quantum chemistry problem on the quantum computer, but instead look at different parts of that chain and see if they can get improvements with machine learning at different components. So yeah, I think we're just in an interesting time where some of the big picture things that everyone's looking a lot at is quantum chemistry, optimization, machine learning, but it's all about experimentation and genuinely testing. So another thing that I would speak to is a really important thing that I think both Wolfram and Q-Control do is you've got to put your software out there. And so if you put your software out there, you put your solutions out there, then people can test it, people can verify, and people can check the conclusions you're making as well. So please, I would also recommend everyone don't just read the papers. Because the one thing I would say that I've been in the quantum industry for this long is the papers on both sides can often have a particular kind of the line that they're pushing through. So go and get on a machine, try it yourself, figure out what's actually going on. It really changes your perspective on the state of the devices compared to just the literature. Yeah.
Related to your point, like, in fact, like, the main reason that I mentioned, our summer school is this is like, 3 weeks intense program that we want, like, everybody to basically do a computational experiment. Okay, like, sometimes, like, some of the students, they will tell us, like, okay, what's going to happen? And our response is, nobody has ever tested that. We really don't know, like, if we combine, like, this quantum algorithm plus this, chemical synthesis, what's going to come out of that? These are, like, the experiments, computational experiments that nobody has explored. And one beauty of, like, I think the tool sets that has been developed by you guys and also Wolfram Research for more than 35 years is we want to provide that environment for anybody. Just go and do those computational experiments. And nowadays, like, one thing that is great about quantum technology is at the very end, you can also interact with the real hardware, because most of them are available through cloud services. So, like, you can have your own algorithm, and then really, like an experimentalist, you can run it. Even how fancy or how complicated is, like, algorithm, you can still run it in an actual computer, hardware computer. So I think, like, we are in a moment that we need more of those experimentations. I fully agree with you. And this is like uncharted territories, and we are inviting everyone, especially students, like, when they want to learn quantum computing, especially quantum applications, just go there and do those experiments. Like, I think, like, we really need to be open-minded, and we need much more developers developing true quantum algorithms.
Yeah, I agree. And I guess the other thing is, and it's hard. So don't get me wrong. It's like the thing that we're trying to offer, to help it be a bit easier, you want to be fast, so you want to iterate quickly. So FireOpal and Wolfram, I think that's the thing we're trying to also offer, is the ability to learn quickly. But I would say there's a lot of still unknown questions also about, like, how you really assess the quality of your results. So there's been a long history in academia of using certain techniques on experiments. But I think one thing we've learned at Q-CTRL a lot is that they're so expensive. So the techniques which are kind of standard for testing quantum computers, there's sometimes controversy. So, for instance, quantum volume has gone in and out of fashion depending on who you talk to. But in practice, quantum volume is also something that's not achievable by the average user because of just the huge amount of executions that's required. So there's also really interesting challenges to figure out if you're even just trying to assess the quality of your outcome. So just asking, is this working? How do I know it's working? And there's still opportunities to develop techniques for yourself, or techniques that would help other people in that space. So I do want to also speak to, it's not just about solving the problem and trying to beat a classical computer. There's actually a lot of things to learn on the lowest level of just, like, verifying or defining what success means when it comes to doing that comparison. That's, I think, still a pretty open question too. So yeah, I think it's important to try on real devices, and it's all important to also, everybody needs to keep trying to figure out, what it means to have an advantage, or what it means to be correct or incorrect on a quantum device. It's still something you've got to learn and practice. Yeah.
I think, like, both of us, like, for our audience, both, Q-CTRL and, Wolfram Research, like, we care a lot about, like, education and training, like, the future workforce, especially on emerging technologies. Like, we have AI, we have, quantum, and who knows, like, what's going to come next. Especially talking about, like, education, this was a conversation that we also had with our partners, like, Q-CTRL. We noticed some sort of, like, unbalance in terms of, like, the gender unbalance in terms of, like, developers, researchers that we have, especially on quantum. So I would like to take this opportunity and invite, like, especially, like, girls, women, please, like, interact with both companies. Like, both of us, we would love to see more usage of, like, technology. We would love to help, especially, like, girls, women, on get your hands more dirty with, like, learning these technologies. And this is basically one of the missions that we have. So make sure that you guys, reach out to both companies, and we will be more than happy to help.
Yes. And for those in Australia as well, we at Q-CTRL work alongside Quantum Women is a great organization in Australia, which is a resource where you can meet other women in physics, quantum, STEM, and it just gives you an additional network to work with to figure out where the best jobs are, where the best places are to contribute. And so, yeah, I would highly recommend that as an organization for people in Australia as well. Yeah.
Excellent. So looking at like, the questions from our audience, like, we managed to address like, all of them. So Michael, any concluding remark, anything else you would like to share with our audience?
No, I think the theme of just try it. I think that's the main thing I'd
Awesome.
tell everybody is, yeah, get on Wolfram, give it a go and see what you learn. Yeah.
Thank you, Michael. Like, I really enjoy our conversation. A lot more to learn, like in our audience. Remember, like, as Michael said, quantum is a difficult problem, but it doesn't mean like, we cannot be smart. We can come up with the smart approaches. And there are a lot to do. You'll be surprised how much like, open problems are in quantum. And of course, the interaction between quantum and other topics, such as like, quantum plus LLM, quantum plus AI, these are like, highly hot topics that like, both sides, like, we are actively exploring them. If any interest, please reach out to both of us, Wolfram, our partner, Q-CTRL. We are committed, both academia, outside of academia, and we would love to hear from you guys. So I'm going to hand over to Yi.
Hi, everyone. If you have any comments, suggestion about our live stream, or you want to find a woman to talk with, please follow our LinkedIn page, and you can reach out directly to me. We can talk about like summer school or project can cooperate, or you want to be part of our live stream. We are looking for people to join our conversation. So as you can see, we post our like upcoming events here. Actually, we will go to the Chicago Quantum Recruiting Forum at U Chicago this Thursday. So if you are there, say hi to us. We can grab coffee, have a friendly
Yeah.
chat about the future of quantum.
And if you guys want to know more about like our partners, such as like, the Q-CTRL, Michael himself and Mo, just let us know. We will connect you with them.
Great.
Excellent. I think, that's a very good point. We can wrap up our live streams. Thanks again, Michael. We really enjoyed this conversation, and thanks for your contribution.
No problem. Thank you all.
Thank you, everyone.